And it looks like you've done a pretty good job with the pre-lab quiz, because you've already sort of recognized what are single replacement, double replacement, that sort of thing. And we've talked a little bit about them in class. And tonight we're going to see them, with a little hands-on demonstration. I am going to show you how to do the magnesium and HCl reaction, because that's a little tricky to set up and get it run properly. Unfortunately, I don't have any concentrated HCl left. So I'm going to have to try and make it work with dilute HCl. So I'm not sure it'll work properly, but I will show you how to get it all set up. So let's get into it. So we're going to be performing 6 different chemical reactions, although you will be responsible for all 7, since I'm going to show you what the reaction that we're not going to do, the precipitation reaction, is basically show you how that works. It's really important that you've read the instructions for these, because like I said, there's a lot of different stuff we're going to be doing. And the most important thing for this lab tonight is to carefully record all your observations. So hopefully you've got like a notebook or something. Just write down everything you see, everything, because that is key to the whole report. So I've got a lot of really bad ones from last term, where when they looked at combustion reaction, didn't mention that it got hot, and didn't mention that there was any light created, which are sort of 2 dead giveaways for chemical reactions being taken place. So we're going to go over, this goes back to the very earliest part of the class. We talked about how do you know whether a chemical reaction is taking place or not. So what we're looking for is for you to be able to see what the evidence is of a chemical reaction in each instance, and then know what the chemical reaction is and be able to tell us something about it, because you're going to have to write a balanced chemical equation for each reaction that you see. Okay. Here's some of the evidence of chemical reactions we've talked about already. So the first one is some sort of new product is created that you can see, like a precipitate, which is a solid. That doesn't mean a liquid has been formed out of 2 gases. It means that a solid has been created from generally 2 liquids, but sometimes from a gas and a liquid. That is the reaction you're going to be seeing tonight. So that just means that so a precipitation doesn't necessarily mean that you're going to see this dramatic thing just crash out of solution and fall to the bottom. Sometimes you're going to see a suspension. Anyone tell me what a suspension is? Or give an example of a suspension. You probably had some for breakfast.
Oil and water.
Hmm?
Oil and water.
Oil and water when? Because oil and water separate from each other, right? And oil floats on the top. But it can make a suspension. When is it a suspension?
When it's not emulsified.
Right, yeah, or that's when it's emulsified, that's also a suspension. It just basically means that you have small particles in solution that generally aren't soluble in that solution. And we tonight, actually, hopefully, fingers crossed, we'll be able to make a solid suspension. Basically, when the particles are so small that the density of the water basically keeps them from falling to the bottom. So if you have super, super, super small particles, you'll get this sort of milky suspension. And milk was the example you could use too. Milk
Is
has
that-
solids in it that don't crash out because it's been homogenized or emulsified. And so you have a suspension of solids in a liquid. So
Is
that
that
is
basically it's not dissolving?
right, something that isn't dissolved, but is still a part of that liquid. So yeah, exactly. So that's the first thing we would look for when you're looking for the evolution of gas. If you've got bubbles forming, generally is a giveaway that some new gas is being formed. We've done reaction. We did a titration reaction where we saw a change in pH, or so the production of an acid or a base will change the pH of a solution, and we can see that. That is also related to color change. We saw during the titration of our weak acid, when we added just enough strong base to balance the moles of acid, we saw the phenolphthalein change color from clear to pink. And that was because of the pH change. The phenolphthalein went from being an acid, became a base. And when it's a base, it is pink in color. If we see a reaction absorbing heat, it gets cold, or it's releasing heat, it gets hot. That's clear evidence of usually a chemical reaction. Sometimes it's a physical reaction, but most of the time that's a chemical reaction. And production of light is a clear indication that a chemical reaction is taking place, because that means electrons are getting excited and moving back and forth. And when electrons are moving around, that's a chemical reaction. So if you see light being produced, like when you strike a match or light a candle, which is like one of the really simple chemical reactions, that's a clear indication that a chemical reaction is taking place. So let's review some of these. So the very first one we're going to be doing is a synthesis reaction. You're going to be using steel wool. And what's going to happen to the steel wool? What is the synthesis reaction for that one? What's the reaction for the steel wool? What are we synthesizing?
Is it iron?
Iron, right? So iron is what we're going to be, iron is one of the reactants. What's the other one?
Is that the experiment where you cause it to like rust?
Mm-hmm. So if iron is one of the reactants, what's the other reactant?
Would it be salt?
Mm,
Or
nope. Something you don't even.
Oxygen?
That's right. I was going to say it's something you don't even need to add because it's already in the room. So yeah, oxygen is the other reactant. And you're going to be making iron oxide or rust. Exactly. And you're also going to note, what is it you're going to be, not only going to be noting what the color change is, what's the other indication that a reaction is happening with the iron rusting? Something else is going to be telling you that there's a reaction taking place. What is it?
Temperature change.
Yes, big time. Yeah, you'll be surprised, I think, when you see how much the temperature increases. It gets really warm. I've seen it go up to like 40 degrees in some instances. So basically, that's a rapid reaction, not as rapid as when we actually burn it a little later on. That's even more rapid. But yeah, so that means it's an endothermic or an exothermic reaction.
Exo.
Exothermic, exactly. Excellent. So the second type, so that's a synthesis. That's you take two separate things, you bring them together and you make a new thing. And a decomposition is exactly the opposite. That would be you take a thing and you break it down into two different things. Really common example, and one we're going to be using tonight, is bicarbonate, or in this instance, carbonic acid. Carbonic acid will break down into water and CO2. This reaction is reversible, but we can force it along a little bit by adding bicarbonate. So if we add more carbonate, basically what we're doing is we're pushing the reaction toward making more products. And another example is calcium carbonate. If you heat calcium carbonate, it actually breaks down into calcium oxide. It also releases CO2. A lot of decomposition reactions are pushed forward by making gases. And the reason they get pushed forward for making gases is that once a gas is produced, it leaves, right? It's not like we're breaking it down into like a liquid breaking down into two other liquids, and then they're still in contact with each other. Then the reaction can go backwards. In a decomposition reaction where a gas is produced, basically it can't go backwards because one of the products escapes. And we know that if this is a reversible reaction and we reduce the concentration of one of the products, that pushes the reaction back to making more products. So that pushes the reaction forward. So the single replacement reaction, this is a really cool, it's one of my favorite reactions because it makes a fun product. Single replacement reaction I'm going to show you how to do is the hydrochloric acid and magnesium reaction. So we've got hydrochloric acid plus magnesium, and the products are H2 gas and magnesium chloride. So basically we're going to have some, hopefully you guys have some concentrated HCl. You're going to want 1 molar HCl for that reaction. And you'll notice when it comes in contact with the magnesium, bubbles instantly start to form. And those bubbles are hydrogen. And we're going to see the hydrogen being produced. We're going to do this reaction under water, which makes it even more fun. And the gas will displace the water out of the tube. So I'll show you how to set that up. Because we're going to want a hole in the bottom of the tube, because if we don't, it's going to pop. So we're going to fill the tube with liquid, with HCl and water, and then turn it upside down so it comes in contact with the magnesium, and the reaction should start. Put it underwater, and as hydrogen is produced, it should force the water out of the tube until we have a full tube of hydrogen, and then we're going to blow it up. So that'll be even more fun. So the double displacement reaction is basically, I like to call it the do-si-do reaction, so they change partners. So if A is coupled with B, they come apart, and then C coupled with D, they come apart, and then they switch partners. And a lot of the time we see a lot of precipitation reactions this way. Basically what will happen is that A will be soluble in the presence of B, C will be soluble in the presence of D, but A won't be soluble in the presence of D, or C won't be soluble in the presence of B. When they come together, they precipitate. So you take two solutions, like in this instance, sodium chloride and silver nitrate. When they're apart, they're completely soluble in water. But then when you put them together, once silver comes in contact with chloride ions, boom, they crash right out. So basically, what we're dealing with is free A ions, free B ions, free C ions, and free D ions. They don't really replace each other, because if they're in solution, everybody's just floating around minding their own business. So what happens is that we have two spectator ions and two ions that are not soluble when they come in contact with each other. But we call it a double replacement. And then combustion reactions, I think you pretty much know how combustion reactions work. Now that we're dealing with hydrocarbons, you can see that when we burn hydrocarbons, if we burn them cleanly anyway, we should get carbon dioxide, water, and energy. In other words, we should see increase in temperature. We should also see light being given off. So it's a rapid oxidation. When we see a rapid oxidation, we're going to call it burning. So not only are we going to burn a typical hydrocarbon like a candle, we're also going to burn iron, which you may not have seen before. Iron burns too. In fact, pretty much all metals will burn, because all metals will oxidize, with a couple of exceptions. If you make the metal particles small enough, they will burn rapidly. In fact, magnesium, we should be careful with the magnesium. Magnesium, if that comes in contact with a flame, burns with a tremendous amount of light and very, very high temperature. So yeah, magnesium burns tremendously well. So does aluminum, for that matter. So we're going to need a ton of stuff for this lab. So like I said, I'm going to try and do the precipitation reaction myself. That's lime water. Anyone tell me what's in lime water? What's in there?
Is that a type of calcium?
It is calcium. Calcium and
Hydroxide.
calcium hydroxide. That's right. Excellent. So calcium hydroxide is not terribly soluble. It's just barely soluble at room temperature. But when we put CO2 in there, you get calcium carbonate. And calcium carbonate is limestone. So that ain't soluble. So that is the suspension, hopefully, that we'll see. So I'll try and do that reaction for you guys, but I will show you how it works and the reaction that actually takes place. You will need like the big, probably not the big rubber stopper. You will need the small one. Steel wool, rubber bands, mini spoon, yeast, wooden splints. I couldn't find any wooden splints. Anyone still have wooden splints in their kit? Hopefully you still do. If not, then matches will do. But there's a couple of tests we want to do for gas involving wooden splints. We want to test for gas with a flame, and we want to test for gas when the wooden splint is glowing. So if you don't have these in your kit, you can use wooden matches if you have wooden matches in your house. Like I said, I couldn't find any. We're going to need peroxide. That's a fun reaction. The peroxide and yeast is a good one. Vinegar. What are we going to be using the vinegar for?
The steel wool.
For the steel wool, what is it going to do?
It kind of like strips the coating.
Right, exactly. There's going to be like a thin, like sort of ironically, there's going to be a thin layer of iron oxide actually on the steel wool. And for continued reaction to take place, they're going to have to remove that. So once that's removed, then even more oxidation can take place, because basically you will have removed the iron oxide layer and left pure iron there for the oxygen to go in there and start rusting it out. So yeah, you will need the concentrated hydrochloric acid. Hopefully we still have some left. Magnesium ribbon, a couple graduated cylinders. The beaker, you're going to need the large plastic beaker to do the HCl and magnesium experiment. Candle, small glass test tube. You have a whole bunch of, you have a big glass test tube and you have a bunch of plastic test tubes. You need the small glass one. It comes, I think I found it this afternoon. It's like wrapped, really tightly wrapped in bubble wrap. Took me a minute to find it. Hopefully you've found that. And large polystyrene test tube. Also the forceps, test tube rack, ruler, thermometer, matches, paper towels, scissors. I mean, ton of stuff. A timer, of course, if you have your phone with you, you've got a timer, and your cell phone to take pictures. So you want to take a lot of pictures of these reactions to include in your report. So these are the ones we're going to do: synthesis, decomposition, single replacement, double replacement, combustion. I'm going to try and do that one for you, and then the final combustion. So 1, 2, 3, 4, 5, and 7. Okay. And there are questions in the report to answer for each one of those. So I want you to use the report files. There's a Word file, and there's a PDF file. So why do we use the wooden splint? Why do we need them? We want the wooden splint because sometimes you want it to be burning, and sometimes you want it to be just sort of glowing. Like you'd set it on fire and then blow it out while it's still red. Test for gas. So the 3 gases you're going to be testing for is oxygen, and that's when you set it alight. It's then blow it out. It's still red and glowing. And if you put it in the presence of oxygen, it'll reignite and start burning again. So that's looking for oxygen. For hydrogen, you want a flaming splint or a match. And basically you're just going to be combusting the hydrogen. And it gives a really cool sound. It makes this bark or pop or squeak noise. It's pretty loud. So be ready for it. And that's just hydrogen burning with oxygen and making water. And then for CO2, we also want the flames. If there's CO2 present and you put the flaming splint in there, it should go out. So that's a test for carbon dioxide gas. So 3 different gases we're looking for. Now, 2 of them we want it to be burning, and 1 of them we want it to be glowing. So here's the lime water reaction. Like I said, we had a lot of trouble getting this to work, so I'm just going to try and do it myself. But you can use this as saying, yeah, this is what it looks like when the reaction takes place. So calcium hydroxide is the compound in lime water. So we know calcium's got a +2 charge, hydroxide's -1. So the balanced ionic compound is CaOH2. Now, when that is a base, because it's got the hydroxide, right? So CO2 in the presence of water makes H2CO3. This is carbonic acid. So basically, we also have an acid-base reaction happening here because we have calcium hydroxide and we have carbonic acid. And so when carbonic acid and calcium hydroxide come together, you get an acid-base reaction. These two hydrogens get stripped off by hydroxide ions, leaving CO3, carbonate. Calcium is not soluble in the presence of carbonate ion. And so you get calcium +2 and carbonate -2 come together and form an insoluble compound. And that is what it looks like. This is the suspension that I was talking about. If you leave it long, if you left it overnight, eventually you will, fall to the bottom, but it takes a long, long time for that to take place. So you get this sort of milky suspension. So I'm going to try and make that work, though like I said, I make no guarantees. So that's what that particular reaction is. So really important, since we're doing acids, we're burning things. Really important. We got goggles and shoes that cover your feet, tie back your long hair, wear gloves. Like I said, magnesium burns. You don't want to have a magnesium fire in your house. Like this, it burns really, really hot. And if it gets on your skin, I don't even want to think about it. So lime water is a caustic base. Peroxide is somewhat corrosive. Hydrochloric acid, we know, is corrosive. So you don't want those on your skin either. So, wash up and clean up your space afterwards. These are some of the questions you're going to be asked in the report template. So this is why I'm saying it's really, really important to take careful notes of what you're seeing and what you're doing. Because you're going to have to describe a lot of them. And basically you fill out a chart where you describe each reaction in detail. What did you see? What is the evidence of a chemical reaction? What's the balanced reaction? Okay, so any questions before we get started? It's going to take about 5 minutes, and then we'll get all your stuff together, and then we'll get started. I'm not going to do all the reactions with you. Some of them you can easily do on your own. But I do want to show you how to set up reaction number 3. I believe that's a single replacement. And then I'll, try in vain, hopefully not in vain, to do number 6. So 5 minutes, we'll come back and get ready, okay?
Sounds
All right.
good, Professor.
All right, see you then. Record this part, oops. Yeah, then the reaction starts to pick up, starts to go a little bit faster. Right now, I've got about half the tube is empty. Not empty, of course. There should be hydrogen gas in there. If it was empty, it wouldn't be pushing the water out. This is the same reaction we do when we're trying to determine the gas constant, R. There's another experiment that we did last term with my 210 class, where we took a very precise, we measured the amount of magnesium very precisely, and then produced gas from it, calculated the volume of the gas that was produced, along with what the pressure was and the temperature, and we figured out the value of R. It's a really good experiment. It works pretty well. So this should actually work. This is looking great. So it's almost full of hydrogen by now. So so Renee, you seeing the bubbles around the metal?
Just very little.
Yeah, give it some time. Oh, whoever was using dilute HCl, is that working?
I haven't gotten that far yet.
Oh, okay.
Yeah.
I can't see if it's, I still have a bunch of metal left, so this reaction's still going. Yeah, and the tube is almost completely full. Yeah, I love this reaction. I don't know, for some reason, it's one of my all-time favorite ones to do. Now, what you don't want, so when it's filled up, what you don't want to do is turn the tube right side up, because then hydrogen is much lighter than air and will completely disappear. So you want to keep the tube pointed down and keep the hydrogen in there.
The stopper we use is the smaller one, right?
Yeah, it should fit in the glass tube and it should have a hole in it.
Okay.
Yeah,
So Professor, just continue adding water until it fills the small tube.
right. Yeah, so first you put like about 3 mils of the 1 molar HCl and then tip it. You tip it to the side and then just slowly add water to it. Try not to mix the water and the HCl too much. The idea is you want the dense HCl to keep together so that when you turn it upside down, the denser HCl will sink to the bottom and then start the reaction.
Can I see how your stopper fit in? Did it plug from the very top? Because I just want to make sure I have the correct, because it's the same ones
Yeah,
that we use.
not much of it should poke in. Can I see it?
Yeah, but you see how it, like, mine's going all the way in?
Oh yeah, that's
The wrong test.
that's the wrong tube, I think.
Okay.
Is that plastic or glass?
Yeah, I think she's using the plastic one.
Yeah,
you
I
want-
just
you want
realized
the
I didn't have
glass.
black one.
Yeah, look around for it. It took me a while to find it. It was basically it looked like this. It was like wrapped up in
Okay,
bubble wrap.
I'll be back then.
All right, so this thing is now done because it's all the hydrogen's been pushed out. I still got plenty of metal in there. Maybe I could try it again. So you see that my tube doesn't have any liquid in it. So the gas has pushed all the liquid out. I just put my finger over the bottom of it and basically trap the hydrogen gas inside. Now, unfortunately, I don't have any wooden splints. I do have a lighter around here. You hear that little pop? I don't know if it'll do it again. That was cute. I think that was all of it. Yeah, this makes this little poop sound. I think it would have been a little louder. I think I may have let some of the hydrogen escape. But that's what you're looking for. You're just looking for that little pop sound. Sometimes it's like a chirp or a tweet. Here, see if I can get this to work with the more dilute stuff. Whoop. No. Trying it with the dilute HCl, I got a bubble. Yeah, I think with the dilute HCl, it will work, but it's really slow. So you may have to leave it, let it sit for a good long time. Oh, there it goes. Yeah, it will work. If all you have is the dilute HCl, it will work. It's just slow as hell. So
So if I swapped out into the glass one, it's gonna cause too quick of a reaction, right?
sorry, what was the question?
If I swap out, because I found a glass one,
Mm-hmm.
but I already filled it in the other one, it'll change the reaction too quickly, right? Is that what you were saying? Because you want to have that layer of the water on top.
Oh, it'll still work. Yeah, just pour out the contents of the plastic tube into the glass one and then just, yeah, go ahead. It won't be as dilute as what we're doing. I mean, with the 0.1 molar is much more dilute. You have like so you'll have like 3 times the concentration. If you have 3 mils of 1 molar plus about 7 mils of water, that'll be about 300 millimolar. I've only got 100 millimolar here. And it still works. It's just really, really slow. So basically you can just put it to one side and just, I'm just going to put it over here. Just that reaction will probably take a good 20 minutes to complete. Yeah, actually it's a nice representation of how kinetics works. We're not going to do kinetics. Anyone know what kinetics means?
Isn't that like movement?
Kinetic, yeah, basically means movement. That's right. In chemistry, it means basically the speed at which reactions take place. And one of the basic laws of kinetics is that if you increase the concentration of the reactants, the reaction goes faster, which makes sense. And that is clearly on display here. Because in the time so far, that much gas has been produced in about 5 minutes. Whereas when I use the concentrated HCl, the tube is pretty much half full in about 2 minutes. So it'll work. It'll just test your patience. So I'm going to try and set up the lime water experiment. You guys can work on the other ones while I'm doing that. I have to make sure I have all the stuff. Lime water. Got my vinegar. Got my baking soda. Actually, this thing might take till like 9 o'clock to completely fill. It is super slow. But you can still clearly see that there's a reaction taking place. I mean, bubbles are forming, just not particularly quickly. Okay, so I've got my lime water in here, about 4, maybe 5 mils. Then this big tube, I've got solid sodium bicarbonate in the bottom and acetic acid in a separate tube on the top. And when I shake it up, it should start to produce CO2. Then I've got the stopper on the top, and then a tube where the CO2 can flow out of. So let's start this bad boy. Oh, there it goes. That is a rapid reaction. So you can see bubbles starting to come through here. I am going to put it in the lime water and should start bubbling. Yeah. The lime water is bubbling. So I'm bubbling CO2. Now, this reaction isn't super fast, which is maybe why we didn't have it work terribly well before. Yeah, so every time I sort of tip this up, I tip more. See, every time I tip this to mix the bicarbonate and the acetic acid, I get a big reaction. Watch. It starts bubbling like crazy. Tip it, starts bubbling like crazy. So I think maybe our problem was we weren't taking enough time to let this take place. But you can already see that one clear indication that a reaction is taking place is what?
Bubbles.
And what do the bubbles mean?
Gas production.
That's right. There's still a bunch of bicarbonate in here, so maybe I might just add some more vinegar just to tweak the reaction a little more. So I'm not sure how much CO2 I need to produce to make this lime water get milky.
And that's the suspension you're talking about, right?
That's right. That's right. So I think I'm just going to add a little more acetic acid. And this could get messy. Yep, there it goes. Yeah, it's starting to go again. Yeah, supposedly this takes about 10-15 minutes to occur. So let me just add a little more and then just let it sit. Oops. Okay, I'm just going to let that sit. See if we get a precipitation. All right. Right, so the question was, if you have a 4.7 pH buffer and you add a drop of sodium hydroxide to it, what happens to the pH? And so part of the introduction to that lab was the idea of an ICE table. And ICE stood for like initial. What are the initial concentrations of everything? Change. What happens to the concentrations of the ions present when you add the sodium hydroxide? And the E stands for equilibrium. What happens to the equilibrium of the solution after that change has taken place? So the initial just stands for what are the initial concentrations of the two things we're concerned with. Remember, we're dealing with pH equals pKa plus log of the concentration of the conjugate base of whatever weak acid we're dealing with and the concentration of the weak acid. And our weak acid is acetic acid. And our conjugate base is acetate in the form of sodium acetate. So it's acetate ion. So initial, we want to know how much acetate and acetic acid we have present. Now, I am just going to calculate the number of moles because moles divided by moles is equal to moles over liters divided by moles over liters. This is concentration. But if my liters, if my volume is the same, then I'm just looking at a moles to moles ratio. So that basically saves me a calculation. I don't have to calculate the concentrations, which is fine with me. That's just another calculation I don't have to do, which I am all in favor of. So let's calculate the moles of acetate and acetic acid. So we started with 0.1 molar acetic acid. That's the sort of shorthand for acetic acid. And we had also an equal volume of 0.1 molar acetate. And remember, to make the 4.7 buffer, we mixed them in equal amounts. So we had the same volume of each. So if we have the same volume of each, and we mix them together, that basically means that I've reduced the concentration of both of them by half. Because if I have 5 mils of one and 5 mils of the other, my new final volume is 10 mils. So basically, I've doubled the volume without increasing the number of moles. So I have changed the concentration by 1/2. So my final concentration in the pH 4.7 buffer is 50 millimolar rather than 150 millimolar acetate. Or put another way, 0.05 molar. So half of what it was before. So that's what our concentrations are. What's the volume? Well, remember, on the second plate, we put 2 mils of buffer in each well. So we had 2 ml, and our concentration is 0.05 molar. So 2 ml is how many liters? Get rid of milliliters, and we have 0.002 liters. I warn you, there's going to be a lot of really small numbers in this calculation. So we have a really small volume. So I'm going to replace this 2 mils with liters. 0.002 liters. Instead of molar, I'm going to replace that with moles per liter, because that means the same thing. So how many moles is that? It ain't a lot. It is 0.00001. I think that's the right number. Nope, sorry, 3 zeros. Oops, my bad. Moles. So that's moles of both acetate and acetic acid. Because they're both in the same concentration, that's the number of moles of both acetic acid and acetate ion. So what's the change? The change is when we add sodium hydroxide. So 1 drop of sodium hydroxide is about 0.25 mils. And the concentration of our sodium hydroxide was 0.1 molar. So we do the same calculation. How many mils is that? How many liters is 0.25 mils? 0.25 mils times 1 liter over 1,000 mils. Again, it's going to be a really small number. 0.00025 liters. Is that correct? I'm constantly checking to make sure I don't screw this up. Yeah. That's how many liters. Times 0.1 moles per liter. I'm going to replace that number with my liters, which again, itty bitty, 0.00025 liters times 0.1 moles per liter. Well, how many moles is that? It's not going to be a lot. It's going to be, so moles of hydroxide is equal to 0.0000025. Not a lot, very, very small amount. But we're dealing with small volumes, so that's not surprising. So I've got my I've got my initial amounts of acetic acid and my initial amounts of acetate. I figured out what the change is, but in order to figure out what happens to the equilibrium, I need to figure out what change does this acetate do, or what change does this amount of hydroxide ions do? What does that do? Well, let's look at the chemical equation. The chemical equation is, there's acetic acid plus hydroxide ion. There's my weak acid, there's my strong base. When we add a weak acid and a strong base together, we get a neutralization reaction. What's a neutralization reaction? Well, it produces water. That proton reacts with this hydroxide ion and makes water. What's my other product? The conjugate base, which is acetate. And there is a 1:1:1:1 ratio. What does that mean? It means for every 1 mole of acetic acid and 1 mole of hydroxide ion, I make 1 mole of water and 1 mole of acetate ion. So for every mole of hydroxide ion, I remove a mole of acetic acid because I'm titrating it, I'm neutralizing it. So I remove a mole of acetic acid and I increase by a mole acetate ion. So let's look at this amount right here of hydroxide ion. That is the amount of acetic acid that's going to be decreased. That's the number of moles of acetic acid that will be removed from solution. It's also the number of moles of acetate that are going to be added to the solution. So what do I wind up with? She had a faster way of erasing these without erasing everything. Need a big eraser. So if my original amount of acetic acid was 0.0001 moles, I'm going to remove that many, 0.0000025 leaving me with 0.000075 moles. Again, small numbers, and you got to be really careful doing this math because it's really easy to make a mistake. If you have a scientific calculator, it might make it easier for you. I don't. I just have to rely on my own ability to judge zeros. So what happens to the acetate ion? Well, I had the same amount at the beginning, that many moles, but I have added this amount. So my new amount of acetate is 0.00125 moles. So you can see that I have decreased the number of moles of acetic acid by a little, and I have increased the moles of acetate by a little. That's what my new concentrations are going to be at equilibrium. Or not concentrations, it could be the absolute number of moles. What do I do with that information? Well, with that information, I can figure out what the pH is. But how, Professor? By using our old friend Henderson-Hasselbalch equation again. So the Henderson-Hasselbalch equation tells us pH is equal to pKa of the weak acid. In this instance, our weak acid is acetic acid, and the pKa of acetic acid is 4.75, plus log of the amount of A minus over the amount of acetic acid. Well, that is 0.00075 divided by 0. Other way around. Oops. Let me erase that. This went up. So 1.25 divided by 0.00075. So if we do the division, that's equal to 1.667. It's the same as 125 divided by 75. So we need the log of 1.667. So you use your calculator or you go to the website I showed you and figure out what the log of 1.67 is. In other words, what power of 10 do I raise to get 1.667? And the answer is, where is my answer? Plus 0.2217. So the pH is equal to 4.75 plus 0.2217. So the new pH is 4.97. And that makes sense because we have a buffered solution at 4.7. We have added some strong base. So the pH is going to go up a little bit. It's going to increase a little bit, but not by a lot. And so you can see it went from about 4.8 to about 5.0, which is about right. I mean, it went up a little bit, but not so much that we would be able to tell the difference. Because if you remember, if you looked at your plate, the color really shouldn't have changed from 4.8 to 5.0. That universal indicator is not going to be able to tell the difference. It needs to change by like a whole unit or so in order to change the color. So going up by like 0.2 units isn't really enough to change the color. And so that makes sense. Now for the second part, I'm not going to go through the whole thing but what you need to know about the second part is you're dealing with the dilution, the second dilution. So if the concentration of acetic acid and acetate was 50 millimolar in the first buffer you made, and then you dilute it by 4, and then you dilute it by 4 again. So it's the first dilution and the second dilution. The new concentrations will be 50 millimolar times 1/16. So much, much lower concentrations and 16 times less moles. So what you're going to find for the second part is the moles of hydroxide are going to be greater than the moles of acetic acid. So you no longer have an equilibrium. You don't have an equilibrium. You only have an equilibrium as long as there is acetate and acetic acid present. If there's more hydroxide than acetic acid, it's no longer an equilibrium. So now all you need to do is figure out how much hydroxide is left over. So you've added moles of hydroxide. They have reacted with moles of acetic acid to produce more acetate. And then once there's no more acetic acid, then that reaction's over. So any leftover hydroxide, you just use that to calculate the pH. So how do you do that? Well, if you figure out how many moles of hydroxide are left over, your volume is going to be the same as before, 2 mils of solution, and you added 0.25 mils of hydroxide to it. So your final volume is going to be 2.25 mils. You figure out how many moles of hydroxide you have. Moles. You divide it by the volume in liters. What's that? You figure out what the molarity of hydroxide is. But what do you do with molarity of hydroxide? Because pH is 1 minus the log of the molarity of H plus equals pH. What do we do with the concentration? And I've got concentration of hydroxide. What am I going to do with that? Well, you need to remember that this reaction is also an equilibrium. Remember that at any time, water, very, very, very small amount of it is breaking down into hydroxide ion and H plus, and that there's an equilibrium that called Kw, W for water, that regulates how much this reaction goes forward. The Kw of water is 1 times 10 to the minus 14. And where does that number come from? It comes from the concentration, the molar concentration of hydroxide and the molar concentration of H plus. In other words, the molar concentration of hydroxide times the molar concentration of H plus is 1 times 10 to the minus 14. So the concentration of H plus is equal to 1 times 10 to the minus 14 divided by the concentration of hydroxide. So you know what that number is. You can calculate what that number is. And now you can calculate what this number is. And once you have the concentration of H plus, 1 minus the log of that number is the pH. And so you should, since you have extra hydroxide left over, you should have a very high pH. So you should have a pH somewhere between like 10 and 12 or 13, somewhere in that range, like a really high pH. So if you have any questions about how to do that, we can review it on Monday or Monday during office hours, or we can also, remember, we're going to be doing a review on Tuesday. Instead of doing a lecture review and a workshop, I figured we would just do a review for the exam. So if you're still having trouble with that concept, we can go over it again then. But what I would like you to do is go through the text, go through the worksheets, anything that's giving you trouble, send those questions to me beforehand, if possible. And I'll put together all the problems that people are having issues with, and we'll review them all on Tuesday. Okay. All right. So how's the experiment going? Ooh, I should check my my milkiness. Yeah, so it really helps. It really helps if you let the gas accumulate under there and then pop the flaming splint. Then you, yeah.
So is there also a change in the solution too? Because it looks different now. I don't know if that did anything or if it was just because I added more.
Did it go clear?
No, it just looks more like there's more precipitate.
I don't think there's I mean,
Unless maybe something dropped like when I burned it the first
that
time.
could be. I mean, yeah, because sodium bicarbonate
That's
and acetic
probably-
acid, you generally don't see a precipitation because everything is super soluble. Acetate's super soluble. Carbonate is pretty soluble, unless there's calcium or something else around. So if that's tap water, you could have like a lot of calcium in your tap water, and you're sort of seeing some precipitation from that. Are you wearing your goggles on your forehead, young lady?
Sorry, I was gonna write something. They're fogging up.
Yeah,
Like, every
that is a
time I write,
pain.
I can't see what I'm writing.
That's a pain, yeah. Yeah, those goggles in particular, because they seal in. So yeah, they fog up pretty readily. If you just have the glasses, they don't tend to fog up as much, but they don't offer the protection either, so.
Mine from number 3, it slowed down significantly. I mean, it looks like the water's still,
Oh,
like
was
the
that,
solution's
oh, I need to
moving out,
check
but-
mine. Yeah, that's the one with the dilute HCl.
yeah.
Yeah, actually, it's a good, let me check mine, because I think.
I'm
I haven't looked at
just worried
mine.
about the time frame because I can't stay up all night waiting
Yeah,
for this one.
mine's about half filled. And it looks like it's stopped.
Yeah, because mine stopped like where the magnesium strip that's inside. I can see like maybe like a quarter of an inch of it now is like out. But everything
Yeah,
else
I
is
still got
fine.
some magnesium in mine, but yeah, so the tube, so the reaction's pretty much stopped, and the tube is about half, a little more than half.
But it needs to be completely empty for us to like trap the gas with the tube
Let's
on the
see.
table,
I mean, I'm gonna
right?
try. I'm gonna try it
Yeah.
right now. So
Okay.
Let me get my goggles back on.
So were you going to uncork it then and just let
Yeah.
it fall out on its
Yeah,
own?
why not? See how
Okay.
it goes.
Mine went all the way emptied out.
Yeah, if you have the concentrated HCl, it generally will fill all the way up. But yeah, this one's only, so yeah, it's gonna be kind of tricky because you have to let the water out. I don't want all the gas to escape, so I'll just keep it right side up. Actually, it might pop even better because we'll have hydrogen in there and we'll also have oxygen in there. So maybe it could pop even better. But we've done the first part of the reaction. We've seen gas production. We've seen it displace the water. So
Can you put your camera downward a little bit so we can see how you're uncorking it?
I've got my finger over the bottom, and then I'm just going to let the water out, basically. Okay. Now we may get a whole bunch of nothing here. Oh, works.
Okay,
Did you hear that?
yeah,
Yeah, it works.
okay, I'm
In
gonna
fact,
try
it
it.
worked better than when it was full. And I think it's because we got more oxygen. Because remember, hydrogen can't burn by itself. It needs oxygen.
So I can do it freehand with just the lighter and not the splint, like you did it?
Yeah,
Yeah, okay.
sure. Because yeah, you want combustion for that one. Yeah, that was awesome. It worked. It got a much better sound that time. Yeah, it took forever. I mean, that was what, an hour or something?
Yeah, it worked.
Yeah,
It startled me.
it's a really cool sound, right?
Okay, yeah, it sounds like when you pop a cork.
Mhm.
Kind of.
Yeah, it's a little chirp. It's like a little baby bird or something.
Professor,
Yeah.
which one is a glowing splint?
So you
Activity
set it
four.
on fire and then basically blow it out. And then really, really quick, while it's still red, put it into the gas.
All right, thank you.
Yeah. And if there's oxygen in there, it should reignite. Anything else, if it's CO2, it won't do a damn thing. Oh man, you're cooking with gas now. That's a man, take no prisoners. Yeah, so once you got it burning, yeah, there you go. Quick, quick, quick. What happened? Did it oh, that's CO2, right? Yeah, that won't do a damn thing. Basically, you're testing for oxygen, and the answer is there oxygen? No, there's not. So yeah, so put the towel back over it to sort of shake it up a little. Now put the burning splint in. And it should go out.
So that reaction, so there was nothing because of the CO2 and no presence of oxygen. And
Yeah.
then when you light it, then there's presence
Yeah,
of
so you
oxygen.
put a glowing splint in there, the presence of CO2, it's not going to do anything. It's just gonna, it was out, it's going to continue to be out. Basically, CO2 is used as a fire extinguisher, right? So it's not going to reignite something. Oh man, you guys are having way too much fun, ever. Chemistry's not supposed to be fun. So what happened? Did it go out? Yeah, sweet.
Is it supposed to like make a sound?
Not really. No, the only one that really makes a sound is the hydrogen. I think that's why it's my favorite. It just sounds so cute when it goes pop. How you doing, Renee? Which one are you working on?
I think it's 5.
Which one's 5?
Holding the glass tube over the candle.
Oh, right. Okay. Yeah, that one. I mean, yeah, basically, if you hold it too close, you're just going to get it all filled with soot. But what do you see? Are you seeing like small droplets appearing in the inside of the tube?
Yeah, like condensation.
What is that?
Is that gas?
Not if it's a liquid. It was a gas, it's a liquid now. So what do you think it is?
Is it water?
Exactly. That is one of the products of a combustion reaction. Like if you're following a car on a cold day, you ever notice when they accelerate, the whole bunch of water comes like pouring out of their tailpipe? That's because it's cold and you have hot gaseous water as a product of the combustion coming out of the back tube, out of the tailpipe. It hits the cold air and then it turns into liquid, and then there you go. A lot of people like freak out and think, oh my God, they're leaking gas all over the place. No, it's just water.
Oh, it's just water. I always thought that was gas because they were.
No, it's just water. You know, it's because you're making CO2, which is not so great, and then you're making water, which, oh, okay, it's water. It's nothing. It's no big deal. Yeah, when I was a kid, I always thought that was gas too. It's like, you know, oh my God, there's gas all over the road. They need to get a tune-up, you know, because they're not, especially, you know, I grew up in Canada where it's like, you know, really cold. So you see it a lot more than you do here.
A question in regards to the car. So with like a hydrogen powered vehicle,
Mhm.
those Toyotas, I always see when I'm driving, I see those cars driving, and I see like I guess it's water that's shooting
Yeah.
out there.
That's the only exhaust it makes is water. So it passes the hydrogen through a fuel cell, and in the fuel cell it reacts with water, and the hydrogen gets passed through a membrane, and when it gets passed through the membrane, it creates electrons, and then the hydrogens give up their electrons to the membrane, become positively charged. They react with the oxygen, turns into water, and then the water gets blown out the pipe. That's the only exhaust is water. Yeah, you don't. That's the Mirai, right?
Right, correct.
Yeah. You don't see too many of them around, possibly because I think there's like one place in the Bay Area to get hydrogen.
Yeah, they don't look as good as the other cars.
Yeah, I mean, it's a great idea. I mean, if you could, the only problem is we can't produce hydrogen cheaply. Basically, the main source of hydrogen is stripping it off of hydrocarbons. So you're still stuck with hydrocarbons. And then it takes a lot of energy to strip the hydrogens off of the hydrocarbons. So that's not the best way to go about it. The best way to go about it would be to get water and just use solar electricity and split it into hydrogen and oxygen and then collect the hydrogen. But that takes a huge industrial facility to do that. We'll probably do that. We'll probably do it that way in the future. Because then it truly would be energy neutral, you know. So many experiments that people have left to do. Yes, just get just a tiny, tiny piece. And you basically stretch it apart till I should turn the lights out. That'll be even cooler. Yeah, I'm gonna do that. Here we go. Yes, we stretch it apart till it's super. You want to get as much surface area exposed as possible. And hopefully I don't set my computer on fire. There you go. Like fireworks. Yeah, it's really pretty. And then you're left, you get that same color change. You're left with a sort of this gray color. Yeah, I'm gonna do that one again. So yeah, this one freaked out my high school students when I was volunteering in San Francisco. Because they didn't, because I bet some of them, there you go. It's really cool, right? I bet them that the steel wool would burn, and they would say, oh, you're crazy. And then it actually took their money too. Woo. Yeah, and then you get these tiny little wisps and then gone. Yeah, so make sure you don't do that over something flammable. Yeah, the moral of the story is like, basically anything will burn if under the right circumstances. I mean, there's certain things that won't, but oxygen is pretty damn reactive.
For the yeast experiment,
Ooh, I gotta open the window. Whew, smells like burning metal in here.
so I see where it decomposed.
Mm-hmm.
But I'm just wondering, so is it always going to have that top layer, or is it going to eventually all kind of?
Well, yeah, basically you've made a suspension, right? So you've got the yeast is basically floating on gas.
Yeah, that's
So
how I
until
described
those
it.
bubbles disappear, that's where it's going to stay.
It looks like sea foam kind of.
Mhm. Yeah, exactly. Yeah. So did you tested it for oxygen?
Not there yet.
Oh, okay. Because yeah, you want to cover it with something so that the gas will build up, and then did anyone get that to work with the splint that like catch back on fire again when you put it in the decomposition reaction? Chris, you got it to work? Did it catch back on fire?
Yeah, I did.
Oh, sweet. Yeah, so did you put your thumb over the top of it or something? Of course, you actually have it corked.
No,
There
once
she
I put
goes.
it in there, it just reignited.
Yeah, so you blow it out, Lizelle, and then put it right in there. Do it quick.
For
Reignited?
number 4,
Yep.
when I put the glowing splint back into like the cup with the vinegar, nothing
Mhm.
happened.
Yeah, nothing's going to happen, right? Because what's being produced in that reaction? You got vinegar and you've got bicarbonate. So what gets produced? What's one of the products anyway? One of the products is a gas. What gas is it?
Is it CO2?
CO2. So is that going to increase the likelihood of flammability or what's it going to do?
Nothing.
Nothing. Exactly. So basically you do the same test for all three gases, for oxygen, hydrogen, and CO2. But the CO2 is not going to, for the only sure test of CO2 is the flame going out. Basically, we put the glowing splint in there just so we say we tested for oxygen and it wasn't there. So
I'm
that's
running out of splint.
yeah, basically you could like crack them in half or something. But yeah, basically we do all those tests so we can say, yes, a gas was produced. No, it wasn't oxygen. Yes, it was CO2. That's the main reason for doing that. So you can narrow down your options. Oh man. I got this enclosed room and it's just burning that little bit of iron. Just that's intense. It is really pretty though, so just don't let your kids see it because they'll just be setting fire to steel wool for like, you know, because it is really cool.
For activity 5, I lost my candle. Is there anything else that I can use?
Oh, here you go. Oh, wait. Yeah, I mean, you could use a lighter. You could use, basically, we're just looking for you to collect the actually you could hold it over your stove. Basically what or if you have a gas stove, we're looking for you to collect the products of combustion. And so the candles is basically the easiest and safest way to do that. But yeah, if you've got a lighter or some matches, you can do it that way too.
Professor,
Yep.
for activity number 5, it says carefully pour the gases that are
Mhm.
generated. So do I just insert it in the vinegar?
No. Just well, like it says, really carefully sort of, basically what it wants you to do is see if you can pour out the CO2 and it should like fall down and put out the flame. It doesn't always work because if you've got a lot of airflow in the room, it probably will have, your CO2 probably would have escaped by now. But if you have the cover on it and you got a lot of CO2 in there, like take it off and then very gently, you can actually pour the gas out and it will fall.
I'll try.
Yeah, it doesn't work for everybody. That's another one. Yeah, I tried it and I just basically wound up pouring vinegar all over my candle. And shockingly, it went out. So
This yeast one is really fun.
yeah, it happens quick, right?
Yeah.
I mean, that gives you an idea of how fast enzymes speed up a reaction.
So the glowing one and then the flaming one, it's supposed to create a larger flame, or is that one supposed to go out?
Well, a flame's not going to go out in the presence of oxygen, right?
No, I mean like, yeah, it's just gonna,
Yeah, it should burn a little more intensely, if anything. But the real test is, can it reignite something? So when it's glowing, it's still burning. It's just like, but at a very low level. And so basically it's another kinetic, reaction where you increase the concentration of oxygen and it speeds up the reaction. And so it goes from burning a little bit to burning a lot.